Chemical Kinetics Lecture Part 2. This lecture is mainly based on the reference book Jespersen and Hislop 7th edition, and the book name is Chemistry, the Molecular Nature of Matter. This lecture is mainly prepared for the students. Hope it will help for some students or others related to education and teaching. Here we are going to talk and clear about rate laws. In the part 1 lecture, we have already learned about the chemical kinetics, factors affecting chemical kinetics and rate of reactions, and also how we can measure the rate of a chemical change. In this section, we will particularly study rate laws and the order of reaction. Rate law is not the same as integrated rate law. Integrated rate law mainly discuss concentration change with time, and the rate law is talk about the concentration of the products with respect to reactants and their concentrations in terms of exponent. So let's start the rate law. What is rate law? The rate of reaction is proportional to the products of the molar concentration of the reactants. Each molarity raised to some power of exponent. That has to be found experimentally, not from balancing equation coefficients. So, that means if we consider, for example, A and B reacts together to form products. So, the rate of reaction can be written according to the rate law as rate is proportional to the products of the molar concentration of reactants, where each molarity raised to some power or exponent, and we can express as like m for big N. So, rate equal to K concentration of A exponent m and concentration of B exponent n. Now, the question, how we can calculate the power m and n? As we already mentioned, this is not about the balancing equation coefficient. Balancing equation coefficients tells us the mole ratios, but rate laws tells us the proportionality to the products of the molar concentration of the reactants, and the concentration of reactants we express as a exponent. So, if we want to calculate the power of this exponent or m or n, we have to do the experiment. But how? We can do the experiment when we run the reaction. We can change the concentration with respect to A or with respect to B. For example, if we double the concentration, and we need to observe the overall rate of reaction with respect to A and B. So, in this chapter, we are going to learn how we can calculate this power mn, and also we will study the order of rate laws or order of reaction that closely related to this equation, and we can calculate also the order of reaction if we can calculate the m value. Before going to the experimental procedure, we need to learn some basics about the order of reaction and this exponent power value. Since the rate of reaction is proportional to the product of the reactant concentration, where the concentration expressed as a molarity and exponent, here the number of exponent determines the order of a reaction. In chemical kinetics, we have different types of order. In right side, we can see the zero order reaction where rate equal to K. It seems this zero order reaction is equal to actually concentration independent. So that means if the power m value is 0, then we will conclude that with respect to, for example, with respect to A, then we will consider this reaction order is 0. Next, if the rate equal to K and concentration of K, that means the power 1, we will consider this is the first order reaction. That means when m value will be 1 with respect to concentration of A, then the reaction order will 1 for this concentration of A. Similarly, if the rate equal to K, square of concentration of A, that means the m equal to 2. In that case, we will say this is second order reaction with respect to A, and where the concentration of A in terms of molarity, the m power will 2. Similarly, for the third order reaction equal to K, concentration of A power 3, that means m equal to 3. So when we will found the exponent power m equal to 3, that means this is third order reaction. Now, if in any chemical reaction, let's consider this reaction, the rate equal to concentration of A, concentration of B, and exponent m for A and n for B. So in this particular reaction, then what will be our total sum of reaction, total order of reaction? So total or overall order of reaction equal to sum of each order of reaction. That means the value of m plus the value of n. So that will be calculate the total or overall order of reactant of each reactant for overall order of reaction for reactants in rate law. Let's go back and repeat. Then what happened? What we got here then? So we check it out first that our rate law of reaction is telling that rate of reaction is proportional. Rate of reaction is proportional to the products of the molar concentration of reactants. Each molarity raised to some power as exponent. But do not confuse this exponent with the coefficient. If we change the concentration with respect to different reactants, so in that moment the exponent will be changing and the order of reaction will be also shifting or changing. And we found here that this exponent value is determining the order of a reaction. So if m equal to 1, we will say this is first order reaction, and the rate equal to K, concentration of A. So if we put the 1 value here, so obviously it will rate equal to K. So similarly, m equal to 2, that means this is second order. If the m equal to 3, third order. If m equal to 0, then 0 order. And overall order of reaction with the sum of each reactant's order in rate law. Now let's make this concept little more clear, in that sense that for the beginner it can be complicated. So let's discuss same thing. As I said that we will get the value of exponent m or n by doing the experiment. And how? By changing the concentration. So we can change the concentration or increase the concentration 2x, 3x, 4x and so on. So let's see now here that when we will change the concentration with respect to, like let's consider there is a 3 different experiment we are going to here we saw. So we will change the different concentration of reactants with respect to initial, or with respect to number 1 experiment, or with respect to number 2, 3, 4. So we can find the rate of 5 with respect to 1, like rate of 4 with respect to 1, rate of 3 with respect to 5, like that. So let's see now, go back here and find. So let's consider that there is a chemical reaction whose rate is like that. Rate equal to K, concentration of M, exponent power 1, N power 2, O power 3, P power 0. So that means here the M had the M power concentration of M exponent is 1, that is this is the first order. N exponent 2, this is the second order. Concentration of O exponent 3, that means this is the third order. Concentration of P exponent 0, that means this is 0 order. So overall, or the total order of reaction for this particular rate will be 1 plus 2 plus 3 plus 0 equal to 6. Now look into the right, my rate reaction, the different order. So just imagine the concentration versus time curve. This is x-axis, this is y-axis. So here we go, first order M, second order N, third order O, and P 0 order. Now first talk about the first order reaction. So this is our initial, first experimental value. Now if we increase the concentration twice x, so then how we can write the rate? So that means when we will increase the concentration 2x, that means the concentration of m equal to 2, and we have exponent power 1. So 2 exponent 1 equal to 2. Similarly, if we increase the concentration like 3x, the rate will be also calculating by putting concentration of m3, and 3 exponent 1 equal to 3. Now we can see this relationship with this value. So the rate is proportional to the concentration of reactants. Now for the second order reaction, what we see? In case of second order reaction, if we similarly increase the concentration 2x or 3x and put the value of concentration, so what we are getting? Here the exponent value is 2. We can see here the rate equal to K and concentration of reactants square of concentration of reactants. So that means if we increase the twice x the concentration, and the exponent value will come as 4. So if we double the concentration, the value will be also double. Similarly, if we increase the 3x, it will be 9. So if we increase the 4x, it will be 16 in case of second order reaction. In case of third order reaction, where the exponent or m or n value is 3. So if we put now or increase the concentration 2x, so 2x power exponent 3, the value is 8. Actually 2 exponent 3, what does it mean? That 3 times 2. So 2 multiply 2, so we can actually, I think you all know the basic chemistry. So what we actually it meaning that just 2 exponent 3, that means 2 multiply 2 multiply 2 equal to 8. So actually this is how exponentially the rate and the value will be increased. And if we look here for the zero order reaction, since we know that in case of zero order reaction, rate equal to K and concentration independent, so whatever the concentration we increase, it will not be affected on the overall rate or order of reaction. So anything concentration of any numerical number and exponent power 0, the result is 1. So that means zero order reaction doesn't affect the concentration. I hope now you understand that how we can calculate the order of reaction from the exponent value, which is the molar concentration of reactants. Now let's see some example. Sometimes this is very common during quiz or exam. This type of question comes that they will give you the reaction, balance reaction, and also they will provide the rate of reaction, and they will tell that determining the order of the reaction. So now if we see, so we can do like if we look into the rate of the first reaction, that nitric oxide react with oxygen and produce the nitrogen peroxide. In this reaction, the rate equal to K concentration of nitric oxide exponent 2 and concentration of oxygen. When we will see nothing, that means this is 1. So now if we ask that what is the order of reaction with respect to nitric oxide, so then we will tell this is second order. If we ask what is the order of reaction with respect to oxygen O2, then we will say this is 1. So that means the overall order of reaction for this rate law, for this particular reaction, we can write that 2 plus 1 equal to 3. Similarly, for nitric oxide plus hydrogen reaction, we can see the rate equal to concentration of nitric oxide exponent 2 and hydrogen exponent nothing. Nothing means 1. So here also the order of reaction with respect nitric oxide is 2. Order of reaction with respect concentration of hydrogen is 1. So the overall rate of reaction 2 plus 1 equal to 3. Here if we see 1 plus 1, 2. In this particular reaction is first order reaction. Here is also with respect to NO2 1, with respect to F2 1. So overall 2 order of reaction. Here 1. Now the last one is also C, the ozone plus chlorine O2 and ClO, and this is also 1 and 1, total 2 with respect to O3 and chlorine. But now if we look into this reaction, so how we will explain then? Yeah, we will explain according to the same rule. So here is nothing, that means the order of the reaction with respect to the H2 concentration is 1 and the order of reaction with respect to bromine is half. So total will be 1 plus half. We have to write like that. So I hope now you guys are clear. If you still think you need little more review, you can just go back and check it out, the lecture, and also you can check it out the books for practice. And I got these examples from this website, so if you want you guys can check it out. And yeah, this is just to clear the concept that I already said in the beginning of the lecture, that this lecture is mainly based on the book, and also if I take some other resources, I will obviously acknowledge, and I acknowledge this website. Now let's see how we can calculate the exponent value of rate law from experimental data. We already know how we can do how we can calculate the order of reaction, and even when we change the concentration, as per example. So now we know that what is rate law, what is the exponent, and what type of information we can get from the exponent value. We learn that from the value of m, exponent m or n, whatever the x power exponent we have, we can learn what type of the order of reaction it is. Now we will go for the hypothetical experimental data, and this is from the books that we are following, and the chemistry, the molecular nature of matter by Jespersen and Hislop, 7th edition. So this is the one concentration rate data for hypothetical reaction. Let's consider that reactants A plus B react together and form the product. Here if we look into the table, we can see the number of experiment 1 to 5, initial concentrations for A and for B, and also the initial rate of formation of products mole per liter per second. If we look into the table, we can see that in the first three experiments, we did not change the concentration of B, we keep constant, but we change the concentration of A. If we look into the number 3, 4, 5 reaction, we can see that we keep the constant the concentration of A, but we change the concentration of this value. And for each design of experiment, we have the value. So now we can compare the rate of reaction of 2 with respect to 1 and of course A. Similarly, we can compare the rate of experimental reaction rate for experiment 4 to experiment 1. It can be either for reactants B or reactants A. So now let's see how we can utilize this experimental value, and we can calculate the exponent number. Here the rate 2, ratio of rate 2 and rate 1. So if we consider rate 2, 2 subscription means number of experiment. So rate 2 means constant k. This subscript means number of experiment 2, and this is our exponent power. So obviously, according to the rate law, we can write that for the rate 2, the constant k, concentration of A2 power n, concentration of B2 power m. Similarly, for rate 1 equal to constant k, concentration of A1 power exponent n, and concentration of B1 power exponent m. We can rearrange also the reaction like that if we can nullify this k value. Now what we can calculate here, two things we can calculate, and then we will compare the n value and we will find it. For example, here we have the rate of formation of product for the rate 2 and the overall rate of formation of product for rate 1. Go back to the slide. See, rate 2 4, rate 1 2. This is the overall rate of formation of product mole per liter per second. So that means we can calculate the rate ratio between experiment 2 and 1. See here, when we find the number 2. Now what else we can calculate? Let's see. We have, okay, what else information we have here? We have the concentration of A, concentration of B for the experiment 2 and for the experiment 1. So that means we can also calculate the concentration ratio for experiment 2 and for experiment 1. See here, since we kept constant the concentration of B, we can nullify. So what we are getting then? So mm value are nullifying. So what we having here? So this mole liter per liter mole per liter is also nullifying. So what else we having? We having 0.2, 0.1. That means 0.2 and this exponent n. So that means we have now 2.0 power n. So then what we got? If we look back into the reaction, this is left and this is right side. we find here the left side ratio of the rate 2 and the right side concentration ratio. As we know, according to the rate law, that the rate is proportional to the product of concentration of reactants, where molarity raised in terms of exponent. So now if we combine the left and right part results, so what we have? This side is 2 and this equal to 0.0 exponent n. So this equality is true only if n equal to 1. So this is the thing we have to find it. So if we can find the ratio of rate of overall reaction between the two experiments with changing concentration, either with respect to A, B or vice versa, then we have to then find the equality of the left rate ratio and the concentration ratio. If when we will find the equality, that means we are find the value of exponent and also we finding the order of reaction. So here we saw that if we do the n equal to 1, that means 2 equal to 2. So that means this is the first order reaction with respect to A for the reaction compared to 2 and 1. Similar calculation is done by utilizing the value from the experimental table, and we see here the value. For experiment 2 and 1 we saw. For experiment 3 and 1 we find same first order. For experiment 3 and 2 we find the same 1.5, 1.5 n. That means all three cases, if we do n equal to 1, that means they are the equal, and this is our way to calculate the value of exponent. But now if we look into the ratio between the 4 and 3, let's go back to the table. 4 and 3, what do we have? If we see the 4 and 3, the concentration of A constant but concentration of B change, and the overall rate is here 0.1, see 0.6. And now if we look into here, you can guess that when we increase the concentration, the overall rate increased. How many times? So then we can also guess from here. Is it double? Is it a quadruple or more? But we will see the procedure how we can do that, not from directly guess here. So when we do the only value of n that makes all of this equation true n equal to 1, we saw that. So therefore we can find, therefore see, the reaction must be first order with respect to A. Using the same procedure while choosing experiments where the concentration of A is same. So all the experiment above we saw the B was constant, but when constant or same, when the A will be same, then we will give us exponent on B. So rate of order of reaction with respect to B. So here if we see what we getting, so rate ratio of 4 and 3, the concentration of A cancels since concentration of number 4 reaction and concentration of 3 reaction is same. We did the same thing, see here, as I said. Then what else we have? we have rate 4, rate 3, experiment 4, concentration of B and power exponent m, and similar for rate 3. So if we do the same thing, and also if we do the log, what we are getting, if we convert into log like that, so and then we put the value of the ratio, so what we are getting? So we are getting here, and for example using the data from experiment 5 and from 40, yeah, so what we are getting, 2.25 equal to 1.5 exponent m. How we are getting? And we did the same formula. So if we follow, then log 2.25 m log 1.5, and then if we calculate, we will find the m value is 2. That means this is the second order of reaction. Having determined the exponent for the concentration term, we know that the rate law for the reaction must be the rate equal to K concentration of A exponent 1 and B exponent 2. How we get? Because we already calculated with order and rate with respect A, and we find always 1. When we put n equal to 1, we find the equality. But in case of when we did between the 3 and 4 the same procedure, and eventually we find the m equal to 2, so with respect to B. So now if we want to finally write the rate of reaction with order, so we will write like that, Ka1 and B exponent 2. So also we can write A1, normally we don't write, so that means for the particular reaction that we got in, that we start with arbitrarily, that A plus B terms product that we initially consider for the table value, and the rate of the reaction according to rate law is like that. So this is how we can calculate the exponent value by utilizing our experimental value. So I want to, here the value we find that comes from the same procedure and same calculation when we did by using the data from experiment 5 and 4. So experiment 5 and 4, actually we got this one, like we got for experiment 2 and 1, experiment 3 and 1, experiment 3 and 2. Similarly, when we did for the experiment 5 and 4, we did like that. So if you using this equation and put the value what we get, then we will find the m value. If we have easy, if we see this is very equality, if just n equal to 1, it's come easy, but when it will not, we will follow this procedure and this formula and we can calculate. So I hope you guys understand. As I said, that this is not complicated, but sometimes confusion create because so many things are closely related. Little bit of, we are everywhere talking about the concentration change with time. So as who are the beginner students, I hope it's okay, and if you need review, you can just go back and do, and you can do also practice from book. Yeah, so as I said here, we can see here actually how we get the value. So this is how we can get it. So here, let's see the reaction. So if we write the rate of reaction, we know the rate of reaction with respect to any reactants, the change of concentration per change of unit time. So with respect to BrO3, so what is the rate of a reaction? How we can write the equation? So equal to K, concentration of BrO3, let's consider exponent X for Br Y and for hydrogen ion G. It here, in case of rate loss, we are not going to consider the coefficient. So please remember. So we find by experiment, just the way we finish the experiment and details. So we find that the exponent x value is 1, y value is 1 and z value is 2. That means this is with the rate with respect to BrO3 is first order. The rate with respect to Br bromide is first order, but the rate with respect to hydrogen ion is second order. So then how we can write? We can write like that. And what is then overall reaction? Overall order of reaction is 1 plus 1 plus 2 equal to 4. I hope you clear and like this lecture. So that's all for the part 2 rate loss and the order of reaction. And the part 3 we will talk about the integrated rate loss.